So I need to explain. So at some point, I need to have the fact that a minimal surface of general type has Ks nef and big. Okay, so minimal means in this context you can think of it as saying that there are no -1 curves. Right, so -1 curve is the thing I had earlier on the board, E isomorphic to P1, E squared equals -1. So I'm saying that does not exist, these guys. Right, and then of general type means that some multiple of K is birational. Defines a birational map. Anyway, let me not go into this because I really want to think of this as the definition. Okay, so why do we know this K is an F? So remember, so I have this intersection pairing. And I have the canonical class. Right. Now, if C is an irreducible curve on S, then I have Ks. Sorry, I have C squared plus Ks times C is 2 PA of C minus 2, and the PA of C is H1 of OC dimension, which is greater than or equal to 0. Okay, so you know, if you haven't seen this before, if this is not familiar, then just accept this as an axiom. This follows by Riemann-Roch, or it follows by simple results on cohomology. Anyway, I'm going to need much more complicated things about curves here later. So when PA of C equals 0, this is for a curve on a irreducible C on non-singular surface. Yes, PA of C if and only if C is isomorphic to P1. So this means non-singular and the genus is equal to 0. Okay, so let's think about the possibilities. What happens if Ks times C is negative? Right, so Ks times C is negative and C squared negative. This certainly implies that they're -1, and C is a -1 curve. And that contradicts this minimal. Right? Because these are two numbers that are supposed to add up to something which is greater than or equal to -2. If both of these are negative, then it's negative plus negative is greater than or equal to -2, and that means they've both got to be -1. Right? And so from what I told you, this already gives it. Okay, so what happens if KSC is less than or equal to 0? What happens if I run the same argument? So I'm assuming now no -1 curves. Right, so what happens if KSC is less than or equal to 0 and C squared is well, less than or equal to less than 0? So now there are two numbers that add up to an even number which is greater than or equal to minus 2. And so again, the only possibility is that C is isomorphic to P1. C squared is equal to minus 2, and Ks times C is 0. Right? So these guys are called minus 2 curves. Right? And they're very important. So they're going to correspond later to Duval singularities, or rational double points. So what happens if Ks times C is less than or equal to 0 and C squared is positive? So let me deal with the two cases. So if this is the case, then this implies that H naught of nks is 0 for all n greater than 0. Okay, so why is this? Because if I have a multiple of this, if some multiple of k is effective, then I can multiply it with C. On the one hand, I'm supposed to something get less than or equal to 0, right? But if I get actually equal to 0, then it means that the Ks is numerically trivial. Okay. Either Ks is numerically trivial, or okay, so I mean these are very strong assumptions here. I've got some curve C with C squared positive, so that's something, you know, in this index theorem in the positive part of the cone, and on the other hand it hits Ks negatively. So this means that the Ks isn't just not ever able to grow, to move around, because if it was moving around it would have to hit, it would be some effective divisor, and it would have to hit this curve C positively. Right? So this contradicts general type. And then if Ks times C is less than or equal to 0 and C squared equals 0, then basically the same thing. Basically the same thing happens. Right? If the Ks were ever an effective divisor, then it's got to be an effective divisor that meets this C negatively. So the C is certainly not numerically trivial because it's somewhere in the cone, and that means that Ks would have to be equivalent to a multiple of C. Right? The C is an irreducible curve, so an effective divisor on it is strictly greater than 0, or the curve is. So this would also imply that this Ks, that S is not of general type. Okay. So this, I've dealt here with all the possibilities that Ks times curves are negative, right? And so therefore, for a surface of general type, Ks times C is greater than or equal to 0 for every curve C, minimal. For every curve C, and Ks times C equals 0 only for minus 2 curves. So now, if you look at, if I look at this linear system NKS, then this is supposed to be moving in a big linear system, so defining a birational map. So it moves around everywhere. So this must have nks squared is positive. So I mean, you know, if this is a mobile part, which is birational, right, then plus fixed part f. Then I've got to have m squared is greater than 0. And eventually we prove that ks squared is greater than 0. Okay, I'm sorry, what I'm saying is not tidy, and I'll come back and say it better later. But what the purpose is just to justify this this statement. So from now on, general type, minimal general type. Means, by definition, ks is nef and big.
So what's the difference between being of general type and ks in big?
So you can think of this, you can nef means ks times c is greater than or equal to 0 for all c. And nef and big means and ks squared is positive. Yes? So other people can use big in only the birational sense, but I use it in this sense. Right, this means ks times c is greater than or equal to 0 for all c, and ks squared is greater than 0. Yes. So look, I'm sorry. This is not completely tidy, and of course I could do it better if I'd prepared it better. Right. So Bombiere's theorems answer the question about of how ample ks is. Right, so remember for curves of genus G, for a curve of genus G, we have that 3 kc, G greater than or equal to 2. We have that 3 kc is always very ample. And 2 kc is always very ample if G is greater than 3. Right? And then even kc is very ample if and only if C is not hyperelliptic. So I explained the case of surfaces is sort of this Garden of Eden of algebraic geometry where everything is nice. So how ample is? So what I'd like to say is that Ks is very ample, for, that nks is very ample for n greater than or equal to 5. Okay, it's not completely true. Right, and the reason it's not completely true is because of these -2 curves. Right, so here's my surface of general type S, And then maybe somewhere it has a little -2 curve on it. Or somewhere it has a little configuration of, 3 or 4 -2 curves. Okay, so this configurations of -2 curves are orthogonal to the canonical class Ks. So in other words, Ks times Ci is 0 on all of them. And this means that if I was lucky enough to be able to prove that nks is free, then the morphism contracts the Ci, the C to singularities. Okay, so if you ask, is some multiple of Ks always very ample, then the answer is certainly not, because these can happen. Okay, so there are basically 3 different ways around this. One, I can just assume that there aren't any. Right? So in other words, just assume that Ks times C is greater than 0 for all C. So that's not very good because it's not general. This is not the general case. In the general case, there are a few of these -2 curves. So the second one is talk about embedding modulo the -2 curves. Well, -2 cycle. Let me just say modulo -2 curves. In other words, I can talk about mapping S here to some space P n into some surface X, right? Where I say that the -2 curves get contracted, and the map is an isomorphism outside. Right. So this is what Bombieri does. Well, it's one of the things that Bombieri does. And the third one is to start off by saying, well, the thing we're really interested in is not the minimal model of the surface S. So pass directly to the canonical model, X. So this means i.e. Contract all the -2 curves to Duval singularities. Then talk about nkx on the canonical model. Okay, so I'm making this a little bit complicated, and so what I really want to do is to sort of ignore the problem for today. So for today, let's sort of think about this. In any case, I'm not going to give complete and I'm not going to give complete statements and proofs, at least not today. So I'm intending to give 2 or 3 different proofs and relate the different proofs to other ideas, including modern, more modern ideas. So so the main part of Bombieri's theorem. So Bombieri theorems. So they say that nk on the canonical model X, on the canonical model X. So you know, this is on the canonical model X, R kx is very ample for all x and all r greater than or equal to 5. Right, and then the same thing for all r greater than or equal to 4, provided that kx squared is greater than or equal to 2. And then the same thing, r greater than or equal to 3, provided that pg greater than or equal to 2 and kx squared is greater than or equal to 3. Okay, so you know, I haven't given the definition of what the canonical model is, and I'm not going to give proper proofs of this theorem today. But I want to just say how we're going to start proving this. Right? As I say, this is a big subject. Bombieri did this famous paper in the around 19. I think it was published around 1973, and I and Catanese and lots of other people who work in algebraic surfaces really started our career by trying to understand these papers. Okay, and so you know the intention is I state this theorem here in a way that it looks exactly like this statement, right? And you know, there's a statement about 2kx, and the statement is basically we understand the counterexamples. Right, so 2kx is not very well behaved. 2kx can be have quite funny properties, but basically we understand what goes wrong there. Right, kx is basically hopeless. Right, so nobody expects to get good results about kx. Any bad property you want kx to have, it will eventually have it. Okay. So anyway, this is just an indication of one direction of research that was very important 30 or 40 years ago, and I'm going to at least give some indication about how we do this. Okay, so in subsequent lectures, I'm going to want to talk about these Duval singularities. So you know, approximately 2 lectures on Duval singularities. Right. So the Duval singularities is this kind of picture. You know, if I have a configuration of 4 minus 2 curves meeting there, then they will contract down to x squared plus y cubed plus z cubed type singularity. So this is a non-singular surface containing these curves, and then when I map it down to the model X, I must contract these minus 2 curves because there's the ks is 0 on them. They must get contracted, and they will get contracted down to a point which is locally analytically of this type. Right, and so this is a subject that I have to discuss really at quite some length, because otherwise you don't get the. So you know, this was the beginning of canonical singularities of threefolds and higher dimensional varieties. Okay, but I need to go back to this index theorem. So let me just give a very quick sketch. So we have a criterion for kx plus d to be base point free, or to separate points, or to separate tangent directions so this is what in terms of D being numerically connected, numerically, 2 connected, or 3 connected. Right, so I start off with, maybe I start off with D being in, for example, if I'm trying to prove this, I would start off with D in 3K, and then I need to prove that D is whatever I said here, numerically 3 connected. Right, and so this is going back to what is numerical connectedness. How do I prove numerical connectedness? So that's the thing I want to discuss now. And to do this, I have to go back to this index theorem. So I explained last time, index theorem says the intersection pairing of divisors defines quadratic form, a bilinear form, a symmetric bilinear form on N1 of S. So this is also called the Néron-Severi group. Actually, I'm not quite sure this is called. Maybe there's always a question about torsion and things like this. So this is divisors on S modulo numerical equivalence. And let me just write numerical equivalence. Right? Of index. So which is non-degenerate, and of index 1 rho minus 1. So I'm going to write 1 and minus rho minus 1. So this is this picture, right, where there's a part of the cone here. The thing I'm writing is the cone Q of D equals 0, where Q is just D squared. Right, so there are the divisors here with D squared positive. Right, and there's one dimension of them. And then in the orthogonal of D, orthogonal is negative definite. Okay, so look, I'm sorry, I'm sort of repeating myself, and I'm probably not one-to-one and not surjective. I'm probably not covering all the material. I'm probably repeating some of it quite completely unnecessarily. So I have this pairing. This numerical equivalence is by definition the kernel of the pairing. So therefore, if I divide out by this, the pairing is non-degenerate by definition. Then this is a quadratic form, symmetric bilinear form, on a lattice. It has a well-defined index. So this is, I choose any diagonalization of the quadratic form over the real numbers, and then I'll get some squares and some squares positive and some squares negative. Yeah, and this is the statement, the statement here, right? So the statement I gave last time. So the theorem, as proved, was H ample, then H squared is positive, and H times C equals 0 implies C squared is negative, and C, let me write D. d squared is negative, and d squared equals 0 if and only if, sorry, hd equals 0, d squared equals 0 if and only if d is numerically 0. Right, so these d's here that are numerically 0 just don't appear in the diagram. In this picture is of the lattice n1s after dividing out by numerical equivalence. Okay, so this is a statement that you prove, but the corollary of it is that if A and B in divisor of S generate a sublattice with generate a sublattice of n1s of rank 2 and intersecting the positive chamber, the positive cone. So this just means that AA plus BB squared is positive for some AB. Then, so these are in N1S, so they're not allowed to be numerically 0. No, none of them, they've got to be numerically linearly independent. Then the quadratic form on A and B has one positive and one negative eigenvalue. Right, then the intersection pairing on AB has one positive and one negative eigenvalue. Eigenvalue is not the right word, is it? It's a diagonal. Right, in other words, I'm assuming here that I've got something positive. If I choose the orthogonal of this positive guy, then I've got to have something negative. Right? And so another way of saying this is, so this is a corollary, and this is the really, really useful thing that you need to remember. So remember the proof of the theorem. The proof was saying if d squared is positive, then you can make d be an effective divisor, and then that contradicts h times d as 0. Right? But the way you really use this is if a plus bb squared is positive for some ab, then the determinant of a squared ab b squared less than or equal to 0 and equals 0 only if A and B are proportional up to numerical equivalence. Okay, so if you're doing calculations, if you're trying to prove a theorem, then you want the best way of proving the theorem, and so I explained how you prove this result last time. It's just a consequence of it's a consequence, if you like, of the shape of the Riemann-Roch theorem. Right. So here we're saying this. Here I'm saying this is how we're going to use the result, and we use it always systematically in this form. Suppose that A and B. Suppose I've got a plane here. Suppose I've got a plane in here that actually meets the positive cone. Right? Then I take the thing that's in the positive cone and I take its orthogonal, and the orthogonal will be negative. Okay, and that's just, so you know, if I take a quadratic form and I diagonalize it, then the number of positive and the number of negative diagonal entries is an invariant of the quadratic form. It doesn't depend on the particular basis. That's Sylvester's theorem of inertia. Okay. So what? So what I want is that, what I want to say is that if D is in Rkx, and either R is greater than, something, or K squared is greater than something. So in other words, except for, what I mean here is, i.e. except for very small cases. Then D is numerically two connected. Right, and if I ask about D numerically three connected, except for -2 cycles. Right, I'm not going to give correct statements or proof of this today in any case. So, just so the point to remind you, if C is a -2 curve, right, and I've got D, and I look at the linear system Rkx, right, so I can assume that this moves around a bit, and so this will certainly contain a divisor which is of the form C plus Rk minus C, plus an effective divisor here, right, and then the intersection number of these two will be 2. Right, so the -2 curves prevent, obstruct 3 connected. Right, and that's just as well, because if something is 3 connected, then it will separate the points of the curve. It will separate singular points of the divisor. So you can't expect to do any better than this. Right, so I'm just telling you, I'm telling you the overall shape of the argument. Right, so let me try and nail down some cases of this. I'm sorry, I'm not making this very elegant because I haven't prepared it properly, but in Bombiere's paper and other papers that followed him, this can be done very, very elegantly. So let's look at Rkx. You know, to be definite, we could say, suppose that kx squared is greater than 3, and R is greater than 3. This is just for example. Right, and suppose that, so I take a divisor in there, and suppose that he can be written A plus B. Then what do we know? So kx is nef. So this means that kx times A and kx times B are both greater than or equal to 0. So if what's true for kx is also true for d. D is just a multiple of k, and so therefore d times A is greater than or equal to 0, and d times B is greater than or equal to 0. Right? And so we just write this out. This is A squared plus AB is greater than or equal to 0, and AB plus B squared is greater than or equal to 0. Right, so I can also write this in the form A squared is greater than or equal to minus AB and b squared is greater than or equal to minus ab. So what would happen if AB is negative? Right. So if these guys, if AB is negative or less than or equal to 0, then this is greater than or equal to 0. Right. And if I have inequalities like this, and I can multiply them together, then this implies that a squared times b squared is greater than or equal to ab squared. Right. And that contradicts this statement. Right, so the index theorem says, well, we know that d squared is positive because d is just a multiple of k, and so a plus b squared is positive. Right, and therefore this determinant a squared b squared ab is less than or equal to 0, so a squared b squared is less than or equal to ab all squared. Right, and if you put these two together, you get either a contradiction or you get that, you get actual equality. But equality would imply that a and b are really just multiples of one another. So a is q times d, and b is r minus q times d. And then that again, then ab is positive. Right? These are effective divisors. These are some positive rational numbers, and so so here I am intending that q is in q. Right, and so therefore AB is positive. So this is impossible. So this is impossible. So I'm just using properties of the intersection pairing. I'm only, the main property I'm using is the index formula expressed in this the index theorem expressed in this formula. Right. So the thing you have to remember here is this. This is a kind of universal property of algebraic varieties. If you cut them down to surfaces, then the intersection pairing will have this one positive and everything else negative property, like hyperbolic or Lorentz lattice. Okay, so what's left is a, b greater than or equal to 1. Okay, so if I'm trying to prove that D is two connected, if I'm trying to prove that D is numerically two connected, so to prove two connected, I only have to get rid of the possibility AB equals 1. Right. So what happens if then a squared plus 1 is greater than or equal to 0? And so I have no idea what happens here. The 1 plus b squared is greater than or equal to 1. And what else am I going to write down? So now I'm not allowed to multiply these together anymore because these are negative. Right. I can't say a squared is greater than negative and b squared is greater than negative, therefore. Okay, so what should I be saying? So does this really happen? So you know, if if AB equals 1, then this inequality a squared b squared less than or equal to AB all squared, you know, this is sort of basically quite a strong thing here. This gives us 1 here. So that guy's got to be less than 1, right? And again, if it were actually equal to 1, if I have equality here, then I'm in this case again. Then a and b are just multiples of another, and then a times b is q times r minus q times d, and you can take the minimum of that as a function of q, and you can mess around with these assumptions on with the assumptions here. I'm assuming this. I'm assuming this, and so you know, you immediately get a contradiction, and so therefore one of a squared or b squared equals 0. So I'm sorry, it's less than or equal to 0. Right, but they're also, you know, this is also not so easy, right? So for example, if a squared equals 0 or minus 1, right? I mean, just interchanging a and b, I can assume that a squared is 0 or minus 1, right? So what do we have now? So now we've really exhausted this argument. There's nothing more to do here. I have a squared is 0 and b squared is anything it likes, then a times b squared is always less than 1, and so we've satisfied this. There's not going to be any more arguments there. On the other hand, what do we have here? A squared is 0. So this, I've got this d, which is rkx, right? And d is a plus b, and I'm assuming that a squared equals a squared is less than or equal to 0, and a times b is equal to 1, right? And so what's left? What possibilities are left?
The square of this squaring, this square is square plus b squared plus twice ab.
D squared is a squared plus 2ab plus. Yeah, you see what's I don't. So I'm not quite sure I want to take the square. I think what I want to do is take d times a. Right, so that's the thing I had before. That's a squared plus ab.
Why you said that a squared is 0 minus 1.
I'm sorry?
You said before that a squared is 8 of 0 or minus 1.
Yeah. And they are a. So therefore dA is equal to 1 or 0. Right. So dA equals 0. This implies that k times a is 0, and that means that a is a union, a sum of minus 2 curves. Right, and so the a squared. So a squared is even. Yeah, dA is 0 and a squared is even. Right? But that's not very good. Right? Because it's not possible for a squared to be even and also for dA to be even. I'm sorry. It's not possible for dA to be 0 and a squared to be even. So this is not possible. Okay, so let me try to say this. So we have this thing that a squared b squared. Sorry, ab. The only case to get rid of, to deal with, is, or to contradict, to get a contradiction from, is AB equals 1. Right? So if AB is 1, then A squared, B squared is less than or equal to 1. And so A squared, A squared, without loss of generality, possibly exchanging A squared and B squared, A squared is less than or equal to 0. Right? But then A squared plus 1 greater than or equal to 0 implies that A squared equals 0 or minus 1. Right? So if A squared is minus 1, then then D times A is 0, and this means that K times A is 0. And this is a contradiction. Right, so Ka is always congruent to A squared modulo 2. Okay, so the other case is that A squared equals 0. And so how are we going to get to contradiction in this case? Well, then dA is 1. Yes? But D is R times Kx, and R is, I'm assuming that R is 2 or 3, etc. Right? And so this is a contradiction. Okay, so I'm telling you, possibly in a slightly stumbling way, that we will always be able to say, in all of these cases, in all of the cases where Bombier's argument is going to work, we will always know that D is numerically 2 connected. And basically a similar argument will say numerically 3 connected, except for a number of special cases. So there are always going to be a few special cases here, the minus 2 cycles. Okay? So let me just say in 2 minutes, because I'm going to want to say it in much more detail next time, let me just say in 2 minutes. So if D is nef and big, right, I'm in characteristic 0. And so D is like this, so it's definitely nef and big. And if P is in a singular point of D, then and D is 2 connected, and I'm going to assume here that H1 of OS is 0. So next time I'll explain that you can get rid of this, that you don't need this condition. This was C.P. Ramanujan's vanishing theorem. Then P is not contained in the base locus of Ks plus D. Right. So let me just sketch the proof very quickly. And I'm not expecting you to follow. I'm just expecting you to see the words. Right. So I'm going to write the maximal ideal times OS of ks plus d. Right? And then I'm mapping this onto OS of ks plus d. And then I'm mapping this to the quotient. And the quotient is the quotient is OS divided by MP tensored a line bundle. Right, so it's KP. It's a one-dimensional vector space. Supported at P. Right? So if I can prove that this H1 equals 0, then that implies that H0 here maps onto H0 there. Right? And that means that there's a section, there's an element in H0 here, there's an element there, S, that maps to not 0 element in there. Right? And that's exactly what it means for a point not to be in the base locus. It means that this element S is then a basis of this sheaf near the point. It's an element of the module, it's an element of the, a locally free sheaf of rank 1, which is not contained in the maximal ideal. So therefore it's a unit, it's a basis element. Yeah? And so this goes by the blow up S1 to S. It goes to, I reduce this thing to H1 of KS1 plus D double primed. Right, this D double primed is, so I'm doing F here again, and then this is F upper star D minus 2 copies of E. The 2 copies of E come because I'm subtracting off the MP, that's 1 copy of E, and because KS1 is KS plus 1. Right, and this is dual to H1 of minus D double primed, sorry, of OS1 of minus D double primed. And then finally there's a little exact sequence which goes like this. O of minus D double primed maps to OS, maps to O, D double primed, maps to 0. Right, and when I do this H0 here, I get H0 maps to H0, and then this goes on to H1 here. This H1 is the guy I'm trying to kill. And then this maps onto 0, which I'm assuming. Okay? So, this is a complicated argument, and I've just raced through it here in 2 minutes. So I'm not expecting you to understand it. But this explains why I want this D double primed. Right? This D double primed is something to do with a junction after I make a blow up. So I want this divisor here, so that this divisor here, this singular sheaf, I'm trying to calculate the H1 of a singular sheaf, and I'm doing it by resolving the sheaf, and that there's a little price to pay there, and the little price you pay is this minus 2e. Yeah? And then, so there's a cohomology group I have to kill. I change him by a blow up here into a slightly different cohomology group, and then duality takes me there. This is just ordinary Serre duality for line bundles, for non-singular sheaves, right? And then there's this beautiful little argument here which says, well, this guy was 1 connected, right? He was 2 connected before I blew him up. I do D double primed, he's 1 connected. That's why I told you that in the first lecture, right? So this one has only the trivial sections, only the constant sections. So therefore this map is surjective. Right, the constant sections certainly come from there. And then this maps onto the group I'm trying to kill, which is therefore 0. Okay, so this is the basic idea of Bombieri, Bombieri's argument. Of course, it's you have to do the same argument many times over, and you have to do it much more carefully than I've been doing it here. But this is the argument. Right. All of these notions here. So here I've got a singular sheaf. I've got a sheaf which is not a line bundle, and then I have to resolve it. I do this blow up to resolve the singularity of the sheaf. And nowadays you just say this is something like multiplier ideals or something. And then you're going to see exactly the same phenomena happening in a much more highbrow, high-level combination. Anyway, I'm sure you're all tired, and I haven't prepared this material well enough for it to be completely convincing. But I'll go through this argument again in much more detail next time.